Okay, we've got a couple more cryptography topics coming up, but before we can do those, we've got to do a little bit of math first to support them. In particular, we are going to be looking at primitive roots mod prime numbers. The first thing we're going to do is look at what kind of numbers mod n you can get just by taking exponents of a single number. So you take a single number, look at different exponents, what kind of numbers mod n do you get from that? We're then going to observe which numbers give us the most results mod n. That will lead us to the definition of primitive roots mod p, where p is a prime. And then we're going to work some examples. Alright, so let's go ahead and do some computations mod 8. Nothing special about 8, I'm just going to do a few computations here. So we're going to look at different exponents of numbers. So 1, 2, 3, 4, 5, 6, those are the exponents. So we're going to take numbers to the first power, the second power, the third power, the fourth power, etc., all the way up to the sixth power. So we're going to start with powers of 1. And those are actually pretty easy, right? So 1 to the 1 is equal to 1, 1 to the 2 is also equal to 1, 1 to any power is equal 1, and when you take that mod 8, you still get 1. The idea here being, if I take different exponents of 1, I don't get a whole lot of numbers, I just get 1. What about 2? Well, if I take 2 to the 1, I get 2, 2 to the 2, I get 4, 2 to the 3, I get 8, then 16, then 32, then 64. If I look at those mod 8, I get 2 and 4 for the first two. 8 is 0 mod 8. And actually, if you look at all the ones after that, they're also multiples of 8, so they're going to be 0 as well. So all you get from powers of 2 is 2, 4, and 0. If you look at 3, 3 is a little bit interesting. It's a little bit different than the other ones. 3 to the 1 is equal to 3. 3 to the 2 is 9, then 27, 81, 243, 729. When you take those mod 8, 3 to the 1 is just 3. 3 to the 2 is 9, which is actually 1 mod 8. 27 is 3 away from 24, so that gives you a remainder of 3. 81 is back to 1, actually, mod 8, right? Because 80 is 0 mod 8. And then it just keeps going back and forth between 3 and 1. And when we do 4, we get something similar as what happened to 2, except we get to 0 even sooner, because when we do 4 to the 1, we get 4. When we get 4 to the 2, we get 16. And everything after that, 16 and beyond, is going to be a multiple of 8, which means that we're going to get zeros for everything except for 4 to the 1. So, and some of the other ones are kind of similar. You sort of get to the idea. It looks like some numbers eventually get to 0 and then stop. Other numbers kind of cycle around between different numbers. And that's kind of the pattern that we get in general. So the question is it possible to get all values mod n with just one number and its exponents? Certainly in the examples that we saw here, that is not true. And even if we continued mod 8, that still never quite happens. But with some numbers, we can get pretty close. So let me do an example looking at powers of 3 mod 5. So if I go 3 to the 1 mod 5, that's just going to be 3, and 3 mod 5 is 3. If we do 3 to the 2 mod 5, well, 3 to the 2 is 9, and that's 4 more than 5, which means we get 4. If we get 3 to the 3, that is 27. Mod 5, let me see, 27 is 2 away from 25, so that gives us 2. If we do 3 to the 4, that's 81, and that is 1 away from 80, that gives us 1 mod 5. And then if we go 3 to the 5, that one's a little bit harder to see, but you get back to 3 and you end up cycling around again. So you get 3, 4, 2, 1, 3, 4, 2, 1, etc. So the only ones you get are 1, 2, 3, and 4, but actually that's pretty good. That's every value except for 0. And it turns out that that is the best we can do. So, if we let p be a prime number and we let a be some integer, we say that a is a primitive root mod p. If when we look at the numbers a mod p, a squared mod p, a cubed mod p, all the way up to a to the p minus 1 mod p, that gives us all the numbers 1, 2, 3 through p minus 1. In other words, all the numbers mod p except for 0. And as a theorem, and we're not going to prove this one because this one's actually a pretty hard one to prove, it turns out there is always a primitive root mod p whenever p is a prime. There are some other situations when you have a primitive root as well, like 2 has a primitive root, so does 4, and actually so does 2 times a prime, so things like 10 and 14 and 22, those also have primitive roots, and those happen to be the only ones. Again, we're not going to prove that, and we're not even going to look at those. All we're going to do is look at primitive roots mod p, where p is a prime. So as an example, let's go ahead and find all the primitive roots mod 7. So what we're going to do is we're going to run through all the numbers that we can mod 7 to see which ones, when we take the exponents, we get all the numbers 1 through 6. I should note that things like 0 is never going to work, because 0 to any power is just going to give you 0, and so we're just going to skip that one. Now, as a shortcut for finding these primitive roots, one of the things you might have noticed in our computations in the previous example was if you just take exponents, those numbers can get prohibitively large. And so to get around that, we have a way of sort of getting around that. So if you have a number a, and you're taking that to an exponent, like a to the 1, a to the 2, a to the 3, etc., all you're really doing is taking what you had previously and multiplying by a each time. Now, when I multiply by a whole bunch of times, it doesn't matter if I wait until the end to take my number mod 7, or if I take it intermediately. I could take any number mod 7 in the middle and then just multiply that by a, which is going to be a smaller number than the bigger number. So what we can do is each time we find a power of a, we can reduce that number mod 7, and then to get to the next exponent, we can just multiply by a again, not by the whole big number, but by the reduced number mod 7. And I'll show you how that works in some of these examples that we work out. So for instance, if I'm looking at powers of 1, 1 to the 1 is equal to 1, and now each time I go to the next one, I'm going to multiply by 1. This isn't going to be very interesting because I'm just always going to get 1, right? In particular, since I just get 1, not a primitive root. Now it'll be slightly more interesting for 2, because 2 to the 1 is 2, 2 to the 2 is 4, that's still 4 mod 7. Now 2 to the 3 is going to be 8, 8 is 1 mod 7. So when I go to 2 to the 4, I'm not going to do 16. I mean, I could do 16, but instead I'm going to take that 1, multiply that by 2, and I get 2. Then to get to the next one, I'm going to multiply that 2 by 2 to get 4, and then I'm going to multiply 4 by 2 to get 8, which reduces to 1 mod 7. And you can see that we're having this repeating pattern, 2, 4, 1, 2, 4, 1, etc. In particular, we don't get all the numbers 1 through 6, so it's not a primitive root. This is getting a little frustrating. Let's see what we can get for 3. So we can get 3 to the 1 is 3. When we take 3 squared, that is 9, but 9 mod 7 is 2. When we take 2 and multiply that by 3, we get 6. 6 times 3 is 18. Now 18 is 4 more than 14, which is a multiple of 7. So that's going to be 4 mod 7. When we take 4 times 3, that's going to be 12. 12 is 5 mod 7. 5 times 3 is 15. That's going to be 1 mod 7. And notice now that we have 1, 2, 3, 4, 5, and 6. That gives us a primitive root. If we want to try 4, let's go for it. 4 to the 1 is 4. 4 times 4 is 16, but 16 is 2 mod 7. 2 times 4 is 8. 8 is 1 mod 7. And then what's going to happen is 1 times 4 is 4. We continue with that same pattern, 4, 2, 1, 4, 2, 1, never getting to the other 3. Not a primitive root, because we're missing, what, 3, 5, and 6. And if we go to 5, 5 to the 1 is 5. 5 squared is 25, mod 7, that's going to give us 4. 4 times 5 is 20, which is, what, 6 mod 7? 6 times 5 is 30, which is 2 more than 28. That gives us 2 mod 7. 2 times 5 is 10. That gives us 3 mod 7. 3 times 5 is 15. That gives us 1. And notice now that we've gotten all 6 numbers, 1 through 6. That gives us a primitive root. And finally, for 6, we get 6 times 6 is 36. And 36 is 1 more than 35. And so that gives us 1. 1 times 6 is 6. 6 times 6 is 36 again, which gives us 1. And you notice we're going back and forth between 6 and 1. Again, not a primitive root. So for 7, we get 2 primitive roots, mod 7, 3, and 5. All right, so now I think you're ready to do some computations on your own. Look for primitive roots on the file that's included with this video.